Okay, so last time I think we finished with a proof of the two conditions that are required for existence, and then that the Laplace transform exists in that case. Let's just go through another example, actually another couple. So let's say you want to take the Laplace transform of 2t. Definition says we should integrate from 0 to infinity of e to the negative st. Wow, all these markers are... Markers are not good. Okay. So we get minus 2t over s e to the minus st. Minus 2 over, I'm just plugging in everything. Minus 2 over s squared e to the minus st, using integration by parts. And if we go from 0 to infinity, again, thinking of the limit as t goes to infinity, when we plug in 0, well, when we plug in infinity, that's going to go to 0. When we plug in 0, we just get a positive 2 over s squared. Okay, so some of these calculations with the definition are not very bad at all.
Could you explain how it goes to 0 for the infinity?
Well, because if you plug in, not plug in, but if you take the limit as t goes to infinity of the exponentials here, the exponential goes to 0.
Oh, it goes faster than t.
Right. Does that make sense? So then this whole first term, when you evaluate, you take the limit, it doesn't do anything, it cancels out. And when you plug in 0, this goes to 0, and then here you get 2 over s squared, because e to the 0 is 1. Okay? So some of these aren't bad, and there are some that are more fun. Yes, Carl, we know that you already know. Well, no, it is. He's got the rules from right started. Okay, so start by setting it up the same way. Definition says we do integral of e to the minus st times the function sine 2t. And just like the previous one, we're going to have to do integration by parts. Here, however, with the first example, you could do tabular because you have that 2t in there, which makes things very nice. Here we can't, because no matter what function you set up to take the derivative of, you never get to 0. So we're going to start by doing integration by parts the traditional way. So let's do so we need to identify these 4 things. I'll do sine 2t as u, so then du would be 2 cosine 2t dt. And now the other part, e to the minus st, that'll be the dv part. So e to the minus st dt will be dv. And when you integrate to get v, you get e to the minus st. Okay, so these are the four things we need. And now we just plug in the formula, which says you do what? uv
Minus
integral of v du, right? So u and v is going to give us minus 1 over s e to the minus st sine 2t. So this is the u and the v minus the integral of v du, so minus 1 over s e to the minus st. Then we have 2 cosine 2t dt.
Since it's a definite interval, once you evaluate the first term.
Yes, so here we also need to go from 0 to infinity. And when we do that, let's see, plug in infinity. That's going to go to 0, right? If you plug in 0, you've got to go to 0 both times. Okay, so this whole first term is going to cancel out. So then all we have to worry about is this other integral that we have here. So let me pull some stuff out. Pull out a positive.
Good morning. Today is the start of quarter 4.
2
All
over
students
s.
must go to the field house to get a copy of their new green schedule. They will not be allowed to enter their classes without a new green schedule. Thank you.
Do you guys have new green schedules?
Yeah.
This was a waste of time. I started coming to class and the front desk lady yelled at me and said, "You have to bring paper."
She's just doing her job, don't you know? Okay. So after we clean up what we have here, we get positive 2 over s times the integral of e to the minus st cosine 2t. And now we have to integrate by parts again. Well, this is going to happen a few times this unit, so we might as well go through an example like this that you guys know what to expect. All right, so we're going to let u du v, probably should write give myself more space, but anyway, we'll do the same thing. Cosine 2t, so then this will be minus 2 sine 2t dt. E to the negative st for dv, same with v as before. And now we'll plug everything in. So I'll have 2 over s. And now integral of uv, so minus 1 over s e to the minus st cosine 2t from 0 to infinity minus the integral from 0 to infinity of v du, so that'll be positive 2 over s. Hi. Is it quick?
Yeah, it's really quick.
Okay. I should say no, just out of principle.
2 over s.
Yep.
E to the negative st times
Okay, so where were we? Multiplying v du, so that'll be positive 2 over s
E to the negative st.
sine 2t dt. So let's clean everything up. From the first term, the infinity part will cancel out when you take the limit because it'll go to 0. When you plug in 0, however, you're going to get a negative 2 over s squared, but we're subtracting, so 2 over s squared minus, now I'm just going to clean this up, 4 over s squared integral from 0 to infinity of e to the minus st sine 2t dt. Bless you. So we've gone in a complete circle. Any ideas besides from Carl?
There's a formula.
No.
Nope.
You wouldn't go into circle for the solve.
That's the.
You stop.
What is the whole integral?
That's what I started with. Yes.
Do it again.
Do it again. Okay.
Add it to the left.
Doesn't that equal Laplace transform?
Add to, no.
You can just
Add to the left
Yeah,
side.
is that? I think that's what you're saying, right? So essentially,
Add to the left side.
let's see if we can put it all up here. So if we look at what we did and where we started, this is what we want. So this is another variation of that, right?
Wait, so
So I'm going to write this out again. Here's what I have.
does that equal 1/2?
Bless you. No.
I have no idea what it is.
So this is what I wanted to find, and so far what I've figured out is that it's 2 over s squared minus 4 over s squared times itself again, right? Do you guys see what I'm saying here? So now what you could do is actually solve for it. If we move the Laplace transform to the left-hand side and factor it out, then we would have a 1 plus 4 over s squared equal to 2 over s squared. And let's maybe clean things up a bit. Yeah, let's write this as s squared plus 4 over s squared. So then when I divide by it, the s squareds will cancel out, and we get 2 over s squared plus 4. Okay, so with the trig, a lot of times you're going to have, well, only for this particular section, you're going to have to do this little trick where you do integration by parts twice and eventually factor out what you're trying to solve for so that you can get a formula for it. Okay, otherwise you just keep going and going and you're not really going to get anywhere if you keep doing integration by parts. All right? Make sense? Good. Okay, another example. Let's say I want to do the Laplace transform of 6 sine 2t plus 2t using the definition. No, I'm just kidding. Bless you. We're not going to use the definition anymore. Because we already figured out the transform for sine of 2t just now. And we did 2t, I believe, today as well. So if we just use the linearity property, we could say that this is just going to be 6 times the Laplace transform of sine 2t plus the Laplace transform of 2t. So then we get 6 times 2 over s squared plus 4 plus 2 over s squared. These are the formulas we obtained earlier. So let's clean it up. 12 over s squared plus 4 plus 2 over s squared. Common denominator.
Can you just leave it at that?
Well, you could. 12s squared plus 2s squared, so that's 14s squared plus an 8. The reason I like to write it like this now is because sometimes you're going to have problems where we're working backwards. And you're going to say, well, here's this function. Let's work backwards and figure out what the function's worth. Okay. Okay. One more thing, and then we'll summarize what's going on here. For piecewise situations,
Oh, wait. You just add.
so let's say we wanted to take the Laplace transform of f of t, where f of t is the piecewise defined function 0 and 2. 0 when we're between 0 and 3, and 2 when we are greater or equal to 3. Okay. So when you're given a piecewise example or a problem to find the Laplace transform for, you basically just set up an integral the way it looks like you should do it. So this first integral would be simply from 0 to 3, and this one is going to be from 3 to infinity. So that's the only difference. Instead of going from 0 all the way to infinity, you chop it up according to the definitions here. So we go 0 to infinity. Yeah, I'm just writing it out. This is the definition, and for this scenario, we go 0, 3 first, e to the minus st of 0, or times 0, dt, plus, so we do two integrals, integral from 3 to infinity of e to the minus st, and from 3 to infinity the function is now 2 dt. Okay, so apply the definition. Since it's piecewise, you split it up accordingly. Here we're going to get 0 plus, well, let's actually write it out. So this will be negative 2 over s e to the minus st evaluated from 3 to infinity. So the infinity part gives us the 0. The 3 portion gives us a positive 2 over s and an e to the negative 3s. So our answer would just be 2 over s e to the minus 3s. Okay. So, summary. What's that?
Oh, this is a summary before you go with the rules? Whatever.
Well, this is the rules.
Oh, okay.
Yeah. So here's your little Laplace transform table that you should memorize. And then we'll finish with one example for you guys to try, and then we'll be done early today. This is called Theorem 7.2. I'm not sure really why it's worth being called a theorem, but whatever. All right, so the first transform you should know is the Laplace transform of 1. And that's simply 1 over s. The next one is the Laplace transform of t to a power. And that's going to be n factorial s to the n plus 1 for the denominator. Next one, the transform of an exponential, so let's say e to the at. that's simply going to be 1 over s minus whatever this value in front of t is. D, or the fourth one, is one we just did, the sine of kt. And that'll be the constant k over s squared plus k squared.
How many other?
1, 2, 3, 4, 5, 7, but 5 are the ones that you're going to really use a lot. Next one would be for cosine. And that's very similar, except it's s over s squared plus k squared. I always remember these as opposite of what of phonetically what it sounds like it should be, if that makes sense. Like sine does not have s in the numerator, but cosine is the one that does, and they're kind of flipped, if that makes sense. I know, I look for weird things to remember things by, but maybe it'll help at least one of you. These are the ones that are not as useful. It's not hyperbolic sine and hyperbolic cosine. You're welcome to use them.
No.
You have never learned them, I don't believe.
No, you don't. But it appeared in one problem, except not in the second. It appears in some. I don't know.
Okay, so the hyperbolic sine, the transform of that will be k over s squared minus k squared. And then for the hyperbolic cosine, it's the same, except s over s squared minus k squared. I forget which is which, but the definition for hyperbolic sine and cosine, one of them is the average of e to the t and e to the negative t. And then the other is like the half of the difference of e to the t and e to the minus t. So you get those curves, and that's what these stand for. But we like to call them this.
Sine was minus, cosine.
Sine was minus, so e to the t minus e to the minus t over 2, and cosine was the average. Okay. Again, how do I know that? Because I just remembered them, but I never dealt with them ever. So, yes.
So in the homework, can we just use these tables or do we have to go to the whole problem?
I think there's a couple that say use the definition of the transform. Other than that, you're mostly using the table. Yeah. Okay. All right, one last problem. This is your exit ticket out of class. No. Laplace transform of sine squared t.
What?
You got about 19 minutes. I'm sure you can figure it out.
Is 2 over s squared plus k squared? Okay.
The 2 is right. Yeah. Well, there's clearly a 2 right there, so you know. You don't need to use the definition here. I can tell you that right now.
I don't want to
Why?
I definitely don't. I definitely not recommend it.
Why? I already started.
Don't.
Because you already have these rules now.
So what is
Think about small.
It's 2K.
Oh,
Think about identities.
Okay. Thank you, Carl.
Oh, wait.
You're the best, Carl.
Wait, would it have to? Would it have been a circle? Yeah. You would have been a circle.
You only for chaos.
Sometimes you just
Let's have you actually try a problem in class for once, Charlie. You can do your no cards outside of class.
Well, I don't know the identity, but
Sure you do.
I
You passed Calc 3, right? Well enough.
I'm not
It's one of the double angle
Yeah.
identities.
It's minus.
One
minus.
Minus or plus?
1/2 minus 1/2.
I forgot. Okay.
Cosine is plus.
Yeah. Good enough.
Question. Can you use this one?
Yeah.
That's the one.
Yeah.
Wait, is the Laplace
Stop.
Please scan. It just sounds so goofy.
I know. Like 1/2, or should be 1/2. Is that
Yeah.
how you do it?
Yeah, you just take 1 over s and multiply.
Actually,
Love Laplace.
I got it.
Jesus, so cool.
Okay. Thanks for
Mm-hmm.
suggesting.
Laplace. I like Laplace. It's cosine.
What's the answer?
Hold on, I'll tell you.
Hey, Carl, did you get it? Is it 1 over 2s minus s over 1? 2s equals 6.
Yeah.
Is this? Oh, hey, Carl. You want to check the take home, please? No, I did it. I was kind of circulating, but
No, it's more. Oh, yeah.
I just want to do it.
Are you saying it wrong? No, you're saying it wrong. You told me that.
Are you saying anything?
I didn't send it right. My host did it on solo.
24.
So what's the
21st.
We're looking good, guys. All right.
So, we have like 16
Maybe,
You're on for 20 days.
maybe go straight for this.
20 days before.
It does. I'm telling you, those days that I scheduled, we're actually like 16 hours.
All right, I'll see you guys tomorrow. For those of you that are leaving. Yes. We won 3-2.
Wait, you're going for something, right?
Yeah.
And Stanley is how close to her?
Right across the street.
This was like really close.
One.
Because if she doesn't get birds, then I told her all like, okay, you should have some
It was in
Stanley. Really?
Just like a bird. Everyone wants to live in Georgia than New Dorms.
If everyone else looking like birds, then it'd be hard for her.
Yeah, that's why we're wasting time.
No, honestly, I think you should. That's why. Stanley will be the hardest of all the overclass. Like most of it is overclass.
Is this what you had, Emily?
Yes.
Okay.
Thank you.
Mm-hmm.